Okay, in this example problem, we have a stuntman driving a car off a 10-meter high parking garage at a speed of 20 meters per second. And we're asked how long it takes the car to hit the ground and how far does the car land from the base of the parking garage. Okay, remember the assumption that we're making in these projectile motion, that there's no air resistance or it's negligible. So negligible air resistance. And what that means is that then our acceleration in the x equals 0 meters per second squared, and our acceleration in the y is just equal to g, and that's 9.80 meters per second squared, the acceleration due to gravity. Okay, so the very first thing I want to do for this problem is I want to draw a picture and establish a reference frame. Okay, so I'm going to draw my picture. Here's my parking garage. Okay, here's my car. The top of the parking garage. It's going the wrong direction. Let's just draw the car as a circle. Okay, so here's our car. It's traveling at 20 meters per second. And we're assuming that the parking garage is level with the ground, so this is just purely velocity in the x direction to begin with. So that's our initial x velocity, which means our initial y velocity is 0. So our vy naught, we're assuming, is 0 meters per second if he's driving off of a parking garage, like a level of a parking garage. Okay, we also know that the initial y position is equal to 10 meters. Okay, we know we need to set a reference frame, and if I say that's 10 meters, then my reference frame is going to be here. When I do projectile motion problems or two-dimensional problems, I need to draw like a little coordinate axis to denote where my reference frame is. So I'm going to set 0, 0 right at the base of this parking garage, and my positive y direction will be upward, and my positive x direction will be to the right. Okay. So I want to know how long it is going to take this car to hit the ground. Okay, so once it comes off, it is going to kind of fall to the ground on a path, something like that. So what I'm interested about is where this hits the ground. So here I'll draw the ground. Here's the ground. Okay, so I want to know what time does it hit the ground, and I'll say just TG. Okay, right when it hits the ground. Okay, so there is my picture. I think I've labeled kind of everything that I know. That means, and setting my reference frame here, that means my y position over here is going to equal 0 meters in my reference frame. Okay, I know my initial x position, if I'm right here, and when it leaves the parking garage, that's going to be x naught equals 0 meters, right? And my x coordinate of that position would be 0. Okay, so I have my picture drawn. Next thing I want to do is I want to inventory my variables. Okay, so for projectile motion problems, you need 2 inventory lists of variables. You need the y direction and the x direction. So let's start with our x direction variables, what we know. Well, I know my initial x position is 0. My final x position, I don't know. I need to find that in part B, but I don't know that right now. My initial velocity in the x direction is 20 meters per second if it drives off horizontal and parallel to the ground. I also know, since I have no acceleration, because this is a projectile motion problem, that my velocity at any point is actually going to be 20 meters per second in the x direction. Okay, my acceleration is 0, and the time that I'm going to care about how far, for part B, how far does the car land from the base of the parking garage? Well, that's the same time I'm trying to find in time A. So the time that I care about in this x direction is the time when it hits the ground. So I'll call that TG. Okay, now I want to inventory my variables in the y direction. Okay, so my initial y position is going to be 10 meters. My final y position is 0 meters when it hits the ground. My initial velocity in the y is actually 0 meters per second. If it leaves the parking garage at 0 meters per second in the y direction, it's not going to stay at 0 meters per second in the y direction, right? That y velocity is going to, it's accelerating in the y direction, so that y velocity is going to become greater and greater as it falls. But it does start out with 0 y velocity. Okay, go ahead and get rid of those. Okay, my final y velocity I know nothing about really. I do know my acceleration. In my reference frame, I've set positive to be the upward. So I'm going to set acceleration is negative 9.8 meters per second squared. And a lot of times we just write that as a g for the y direction instead of a. Okay, and the time that I care about, again, is the time when it hits the ground. Okay, so the time that it takes for this to hit the ground, remember this is the x direction motion and y direction motion of a projectile is kind of like uncoupled. You can analyze them separately. So we know in free fall, since we're accelerating downward, that is what's going to dictate how long it takes for this to hit the ground. If there wasn't any y acceleration, if this had an initial 20 meters per second, it would just continue traveling just horizontally parallel to the ground. But that's not the case. We have some y acceleration, and that acceleration due to gravity is what's going to bring that object down to the ground. So when we're figuring out how long something's in the air, really we want to look at our y direction, and our y components can help us figure out how long an object is in the air. Okay, so for part A, I'm going to look at my y position versus time equation. So y equals y naught plus v naught yt plus 1/2 gt squared. Okay, well, my initial y velocity is 0 meters per second. So I know this whole term is going to cancel out to 0. And I know my final y is going to be 0. So that cancels as well. And then if I plug in my numbers, I have 0 equals 10 plus 1/2 negative 9.8 t squared. Okay, so I bring the 10 to the other side. Negative 10 equals negative 4.9 t squared. Okay, I divide both sides by 4.9. My negatives cancel and it's positive, so I take the square root of 10 divided by 4.9 to give me t, and that ends up as, on my calculator, 1.42857, but I want to round to 3 significant digits. So what I report that the time it takes for it to hit the ground is 1.43 seconds. Okay. So that's how I solve A. And now that I solved A, I know that the time is what kind of connects these two lists of variables. Okay, nothing is really the same except for the time. The time that it hits the ground is going to be the same time that it hits the ground here for the x and y. So that the time is what connects it. So once I've solved for that time, I now know this time. I know it hits the ground at 1.43 seconds. Okay. So in part B, I'm asked how far does the car land from the base of the parking garage? Okay, now I need to use my x list of variables to solve this one. Okay, so for part B, because this is constant velocity motion, if I were to use the x equals x naught plus v naught xt plus 1/2 ax t squared. Well, my a is 0, so this whole term cancels out to 0. And I'm left with just our equation that I gave you for constant velocity motion. Remember, early on in the course, we talked about for constant velocity motion, we have x equals x naught plus v naught xt, and that's just derived basically from the definition of average velocity. Okay, so here X is what we want to solve for. X will give us this location. Our X naught equals 0 when it left the parking garage. So we plug in 0 for X naught. We know V naught X is 20 meters per second. And we know time is well, I'm going to carry out a couple more decimal places. I don't want to accumulate rounding error. So I'm going to actually, when I plug into this equation, I'm going to say 1.42857. That's a little ridiculous. I don't quite need that many extra decimal places. But just to kind of show we don't want to use the rounded number here for the time when we plug it in. So what we get is we get X equals 28.6 meters. Okay, so that tells us that this is going to land at 28.6 meters away from the base of the parking garage, and the time that it landed was 1.43 seconds. Okay, so that is this example problem here of projectile motion. Let me see if I can show everything on the screen at the same time so you could pause and check your answer. Okay, hopefully that was somewhat helpful.